And section 4 is going to be similar to our precipitation data section, but now we're working with the land surface temperature. So section 4.1, we're going to calculate our LST variables. And here we're going to calculate a mean value from the observed daytime and nighttime data. So in the data set is daytime and nighttime, and from there we're going to calculate a mean value. And we're going to use quality information that is within the product itself to mask out poor quality pixels. And then we're going to convert those pixel values to Celsius. Then we're going to calculate it into daily values. And as I said, it was an 8-day composite. So here we do a little bit more date trickery to end up with each day in the composite window assigned with the composite value. And then summarizing the value by Woreda with a zonal summary for a mean. That's not rainfall. That should be LST value per Woreda. So going over to the code. Here we have the LST section here. So we do our course data date filter here just to set up so that we make sure we have data to run on. We filter by our region of interest, and we're selecting the bands that we want to work with. Our daytime value, a quality information for daytime, nighttime, and quality information for nighttime. In here, we are creating a mask to mask out our pixels that we don't want to look at that have too poor of a quality of data. Now, the details of what this right shift and LTE are is based on the data product. So if you were looking in the bands information here in the catalog, it tells you what the bits are. So when you're filtering out, you can take a look here and see what sort of things you want to filter. Then we're going to rescale the temperature data. I meant to show that as well. Here under bands, you can see that the daytime has a scale factor of 0.02 and are in Kelvin. So over here, we're going to multiply by 0.02, that's rescale it, and then subtract this value to convert from Kelvin to Celsius. And we're going to do that for both daytime and nighttime. And then create a mean value of the day and the nighttime. And then run this function that we've defined over our course filtered data. Here, we're going to get into some of that date trickery for using every 8 days, that composite window, which by the way, starts at January 1st every year. So that is our base date here. And then modifying that for every 8 days so that we can assign whatever date that we are currently in the correct value of being inside that composite window. In the interest of time, I'm not going to go over the details of exactly how that works, but it's all right here in the code. And then we're going to map that function over our LST data and recreate an image collection. Now we filter, now that we've got our daily data with our mean LST variable calculated, we're going to filter back to just the requested start and end times. Like before, we convert the metadata to grids to summarize. We do a zonal summary using reduced regions based on our WARADAs, producing a mean. Map the zonal function, zonal statistics function over the filtered LST data, and then flatten the results for export. So our third variable that we're calculating is a spectral index, normalized difference water index, NDWI, which is based on near infrared and one of the shortwave infrared bands. It is an index that's sensitive to the water change, excuse me, water content in leaves. And we're also going to use quality information to filter out poor quality pixels and water. But unlike LST, this quality information is going to be in a separate data product that we're going to have to join together. Then, similar to the other two previous, we're going to calculate a daily NDWI and then summarize to our WARADA and prepare for export. So here we're going to do a coarse filter on for date and for our region. We're selecting the bands that we want from the BRDF MODIS data and renaming them something that's a little bit easier to understand what it is. And then we also have our quality data, and we again do some filtering and selecting the bands that we care about along with a water band. So here we need to join the two collections. So we're going to create a join that is based on the end time of both products because we want to match it up by time. We're going to define the join between our in bar here and the QA fields here. And then finally apply the join between the two. Then we're going to define a function to add those QA bands, QA2, that band, and the water versus land flag, and add it to the N bar data. So now we have a merged data set. So now we have the values and the quality information all in one data set. So we're going to create a function to mask out the pixels based on our quality and water land flags. So here for quality, we want, we're going to mask out things with poor quality, and we're going to mask out things that are water as opposed to land, because we don't want to calculate this over water. Then we apply a rescale factor on near and SWIR and map this function over our merged data set here for our filtered variables. From here, we're going to calculate our spectral indices. So this is where we are calculating that normalized difference between near infrared and shortwave infrared. That's this equation, right? Whoops, sorry. That's the equation here. This is a normalized difference, and there is a built-in function in that in Google Earth Engine. We're going to map that function over our image collection. And now we're trying to calculate a daily NDWI value. So similar to the other ones, we create a list of dates, get the list of dates all right. Here's where where MODIS BRDF differs a little bit from the other two. This one, because of clouds, often have missing data for particular dates. So we want to make sure that we have a placeholder when there is missing data so that we can calculate the whole thing. And in our final export, we'll have an entry for that WAR-ETA and date, but just a blank in the value field. So that is partially done here where we're creating empty results, just an empty results, and we're going to use it when BRDF data doesn't exist. So this is just a constant zero image that I've renamed the different spectral indices that we're calculating. Now here, this is ripped from the larger one where we're calculating 5 different indices, but it's not going to matter here. So we create a filler for all dates, but we only use it when the size is 0, i.e. when there's no data existing in the BRDF. Then now that we've calculated all of that, we filter back to our requested start date and requested end date. And like the other ones, we get our day of year and year, do our zonal summary with reduced regions for our WAR-ETAs, producing a mean over the WAR-ETA for NDWI. We map our function over and we prepare our results for export. Okay. So the next two I'm going to talk about at the same time. Section 6 is where we just do a map display where we're going to visualize the calculated daily values, but as a map before we summarize to WAR-ETA. And then we're also going to use Google Earth Engine to create a small text file download, similar to this one, that has our WAR-ETA, our day of year, and our LST or our other environmental variables listed out. The users of the full epidemia system are public health officials in locations where it's not really feasible to download or process satellite imagery. And the script will create 3 different CVS downloads for precipitation, for LST, and for our spectral indices here, just NDWI. And each one might have a different range of data depending on availability. So I had these scripts open too long and I had to reload it here. So it's going to take a minute for the script to run. Here we are. So this is the full script all the way down to the bottom. So checkpoint 6, this is the map display. In the app, you can pick which date to view. Here, I'm just picking hard coding a particular date to look at. Filtering all of our daily results to just those days. Creating a palette to display them, and then adding them to the map. So here you can see Amhara region, and I'm currently displaying precipitation. I could also look at LST mean, where good quality data is available, and NDWI6, which probably blends in with your screen fairly well. But this gives you a visualization so you can look at the data before you export it or as you export it. So over here, continuing on, we are exporting our data to the CSV files. We want to get the information on the requested start date. And so we're going to get info to pull that locally, as well as the end date of when last data is available, because we're going to use these two dates in the file name. So you can see when the file downloads the date range that the date goes to, which may or may not be what the user requested, depending on the data availability. So here we do an export table to drive for our 3 different environmental data sets. And these show up over here in the tasks bar where I can run each of these. And I ran some of these earlier, so let me bring up what those look like. So here's our precipitation data, where we have per woreda, per day of year, and a total precipitation value for that time period that we requested all the way back at the beginning of the code. Similarly, we have the same sort of thing for LST data. And you can notice that in places where LST night data wasn't available, that it's blank, as well as the mean is blank, though we do have the day value. But we are not missing any rows. Every woreda and day of year combination exists in the file, as well as in the last file, our MODIS NDWI6 calculations, where due to clouds, most likely clouds, we weren't able to calculate an NDWI for that particular day in this particular woreda. Now, finally, we've got this exported environmental data. And I mentioned at the very beginning that we use this for modeling malaria. So the information that you pull out of Google Earth Engine can be used as inputs into software systems outside of GEE. So this is in support of epidemia, and we use case data, malaria case data from the Amhara region, from 47 woredas inside the region, plus the environmental data to create a early warning and early detection report for the region. And one of the main outputs of epidemia is the forecasted incidence of malaria in each woreda by week up to 8 weeks in advance, 1 to 8 weeks in advance. Once you've done this calculation, once you have these results from your external program, you can then re-upload the data into Google Earth Engine if you wanted for further analyses or exploration. So the section 8 is a new script to visualize forecasted incidents for Epi Week 30, not Epi Week, sorry. ISO Week 32 from 2018 from our publicly available data, which is synthetic data, and display it on the map in Google Earth Engine. So here, yeah, open too long. Let me just reload that. So the incidents that I'm reporting are per 1,000, and it's broken out into 5 different categories: 0 to 1, 0 to 0.25, 25 to 0.5, 0.5 to 0.75, 0.75 to 1, and greater than 1. So here we have our, which I've left in the comments here. So here we have those results, our forecasted incidents, but I've also put in our observed incidents. So you can see the different 2, 3, 4, 5 different color brackets, and how our forecasted incidents compares against the observed incidents. But this is all synthetic data for the demonstration. The links in the slides about the project, you can download the project to your own computer and run it as well if you would like. So that is all that I have for this chapter.